Hello, good evening. So, my name is Ravelin, and I'm a data scientist at Ravelin. Previously, I worked as a consultant at a Big Data Partnership, and I worked for RSA in the data science team, and I did some pen testing for a company called Insecurity. So I'm a data scientist slash security guy. I'm going to be talking about the security and how machine learning is changing security. So security is a hard topic. It's a challenging problem. And I put this visualization here to show you how many companies are being hacked, are being penetrated by script kiddies. This is just the 2014 onwards. This visualization goes onwards to show you that this is a very serious problem. These companies are paying millions of dollars. They're buying the best equipment in the industry, the IPS, the firewalls, the web application firewalls, everything that the industry is offering, and yet they're unable to beat those script kiddies. In the recent TalkTalk hack, it was a 15-year-old guy or something. So 15-year-old kids are able to defeat the best security systems in the market. So what can we actually do to change that? So we look in data science and security, and it's a very topical thing, and it's evolving. But still, most technologies are very much rules and pattern based. So when you look at firewalls, SIM, IDS, and IPS systems, they're mostly based around patterns that experts create rules. And there's a few things that are starting to change. So we're using, in some IPS and IBS technology, they would use anomaly detection to learn the pattern of usage and then detect some sort of attacks. But they're limited to very specific use cases, and they're not unable to detect the more sophisticated attacks. Another example is spam filtering. So if you ever use spam filtering or DLP solutions, you've probably leveraged machine learning to detect spam. And if you remember the days before spam filtering used machine learning, you remember the Hotmail days of the 90s, spam was a big problem. Now no one cares about it anymore. And Symantec recently added in 2011 to their DLP solution a machine learning based approach. So we don't need to teach them you don't need to manually type keywords to find leaking documents in your emails. You can just learn those based on the documents in your organization. Another topic is fraud prevention, where since the early 2000s, fraud has been found using machine learning algorithms by various companies. And I think the last topic, which I'm going to talk about from my experience at RSA, is detection of APTs, advanced persistent threats. And these advanced persistent threats are attacks that are more difficult to detect than a single event in time. So we're talking about players, these actors that have more resources than you, they have more knowledge, and they would launch attacks that take months and even years, and they would end up getting inside your systems. So how these data science projects are born in security product organization. So you have a room like this, and you have the three sort of people in the room. You have the data scientists, and you have product managers, and you have the managers. And the managers are in a position that they want to sort of sprinkle data science as an added feature to their products. And the data scientists, they want to do interesting projects. And the product managers, they want to make the customers happy. And what you need to do at this stage, if you're a data scientist, you need to be able to get the data that allows you to develop the model that you need. And that's the hardest part in many organizations, is getting everyone to agree on what problem are you going to solve. And solving the right type of problem is not easy, even in security, where you have so many different appliances solving niche problems, but none of them actually solve the entire problem of these APTs. So when you choose the right problem, you have to choose the problem that the users are facing. And you have to ask yourself, what is my user's biggest pain? So if the users are talking about user experience, the user interface is a problem, that's not a data science problem. But you only get to that conclusion if you talk to users, if you engage with them. So it's not a typical data science role to talk to the users, but you'll have to do it if you want to actually understand what problems you should be facing. And the second thing we should be avoiding as a data scientist is avoiding these Google-type problems. So I'm talking about problems that you can solve if you have endless amounts of resources and enormous amounts of computing power, data, and bandwidth. And so Google has been achieving great, amazing things. But if you look at the type of things that actually people care about, so Google Translate is a great. I think the battery is dying here. So Google Translate is a great service, but no one is actually paying for that type of service. So when you find yourself when someone's offering that type of project, you have to say, am I going to change people's life in a significant way and increase their value from our product? So if the humans are not going to use this product, it's not going to work. But also you have to bear in mind, if humans aren't good at solving this type of problem that you're trying to solve, then you don't have labeled data to support this. So in security, in industry, finding attacks is very difficult. So you don't have endless amounts of labeled data of analysts finding attacks because it's a problem that even humans aren't very good at detecting attacks. So you have to bear that in mind when you choose the right product. So if someone is asking you this type of question, can machine learning, or in this case deep learning, learn the language of dolphins? I would always say yes, but that falls by the big but. The but is, yes, we can learn the language of dolphins if we provide us with enough data, labeled data, of human and dolphin language communication. And that's the key point here, is that the scientists say, yeah, we can do that. If you give us the data, if we can collect that data, then we can make it work. So what is a sort of typical machine learning product flow that we design for the specific security use case? So we have a system where it collects data, it generates features, and then runs through a supervised or unsupervised model, and then the model is applied to a chain of labeled events, and then we give feedback back to the system after the users have been reviewing the conclusions of the system. So this is a very typical design. It doesn't include actually the internal process of evaluating the system and learning and designing it, but this is sort of the outline. So when you choose a model for such a system, you have a different constraint than compared to the regular computer science process of choosing algorithms. So this is a comparison that any sort of computer science students might look when they're learning sorting algorithms. So they would look at this list and very quickly could point out which one is superior. So it's very easy to choose the right superior algorithm when they're compared in a simple way. But machine learning algorithms are quite different. So when someone says, can we find advanced persistent attacks in your network data? Can we actually choose the right algorithm? Becomes a very difficult task. Because out of the box, there's a lot of industry knowledge about specific algorithms used to solve specific problems. But in this case, you have to ask yourself, what data do I have to actually support my model generation? This is a visualization made by the guys at the scikit-learn Python package. It doesn't include all the algorithms in the industry, but it just shows you that the key in the decision-making process to select a model is understanding your data. Because the questions they ask you is, how much data do you have? How many data points do you have in your data? And what are you looking for? Is it labeled or not? How many categories do you have? And that type of questions, when you have them, when you have the answers, then you can actually decide on using out-of-the-box algorithm like the ones implemented in a pre-packed package like scikit-learn, or you need to develop your own algorithm. And we chose the path of developing our own algorithm because nothing out of the box would actually meet our constraints where we were facing at RSA. So this is the type of design of a network topology that we're talking about. An enterprise customer, they have an internal network where lots of users bring their own laptops, and we have the internet, and the internet is surrounded by a firewall, and we have a network monitoring appliance that records all the inbound and outbound traffic between our users and the internet. And one of our users went home and got infected by a malware, and we're trying to find that user within our network data. And we have another constraint. We're not actually looking at the inside the traffic. We're only looking at the metadata about the traffic. And we're not using custom parsing technology. So we're not actually looking for specific patterns inside the data itself, but we are only allowed to look at the basic data, the metadata extraction service is already providing us. And for developing of this product, we used EMC's internal data. So EMC is a big company. They have millions of events per day. They have thousands of users, and they allowed us to use the internal data to develop the model. But it means we had way too much data, but not enough label data. So on one hand, we have thousands of users, but on the other hand, we don't have attacks, verified attacks in the network, because the prevalence of attacks is hopefully not very common. So this is a problem, and we chose an unsupervised approach to tackle this type of problem. What kind of approach can you take when you don't know the type of attackers you have? You actually need to find and backport the ideas from specific incidents. So we took a domain found to be malicious, and then we tried to understand why was this domain malicious? Why was this domain part of a CMC network, CMC command and control botnet? And then we started creating these features manually to model the behavior of different domains in the network data. So we would have domains with longer host names, with multiple subnames, domains without refer, used by different protocols. The problem is that most traffic in the network these days is based on the HTTP protocol. Whatever you're using, if you're using chat messaging apps, video messaging, Skype would sometimes resort to using HTTP as a protocol. So you have all these protocols using the HTTP as an underlying protocol. We had to understand what are the nature of each of these protocols to differentiate between them and to generate features that shows specifically the malicious and the risky factor of these domains. So we have sort of basic features that are generated on a per event basis, but we also have aggregate features that are generated when we look at the entire population of all the domains. So these are more normalized type features, like the number of domains by the number of source IP addresses accessing them. And it shows you these metrics of popularity and other specific features we are interested in. So how do we actually compute how do we generate these type of features? So at EMC we had access to the internal system. So they had a green plant database with lots of data, and we used SQL to extract the queries, and we could use Python and R to model to build a basic model to find the data that we're interested in. But when we go for production, RSA is selling an appliance that is using Hadoop. So we had to develop basically two models, one in Python and R, and another one in Java that could meet the stack of the products we're trying to sell. So using Hadoop was used as a storage and computing system. So we could have a dump of all the metadata from the network monitoring appliance dumped onto Hadoop, and then we can run a MapReduce job routinely every hour to extract these features. Every time we extract the features, we compute the scores on a sliding window of, let's say, a week. So we would have the relative score for that domain in the last week. And then we could write these scores to a database and show them to the users, and then the users could label them, and also could tell us if they're interested, and they could investigate them, and they could alert on them, and they could do more investigation processes inside the RSA security analytics appliance. So before actually the scoring, we have to do some normalization stages. So first of all is the number of bins. And in this visualization, I chose 100 bins to show you a histogram of two randomly generated features. This is not actual data, but this should show you the point that the number of bins is important when you're trying to show a histogram. And we want to show the users a histogram of a single feature in time. We have to choose the right number of bins. And if you don't choose the right number of bins, you might end up with a very simple histogram of 10 bins, which might look nice on the screen, but might not give you enough information. When you create automatically the number of bins, you might end up with 2,000 bins. So you have to use the right algorithm to generate the number of bins in your histogram when you do it. And after that, when you do normalization, you need to understand that your data has different scales, but you also have directionality. So if you look at number of users accessing a domain and you just apply a normal anomaly detection algorithm, then the most popular domain would be Google, would be anomalous, because it's so by far different than any other domain in your population sample. So each feature would have both a normalization function applied and a directional applied to it. So you could know all features actually, all the scores of each features, the normalized scores are in the same direction. So when you actually score them, you can sum up, or you can use a product of all the scores and then get a single score to represent a single domain. And what we did is every time you run a batch job, we score all the domains in our window, and we rank them up based on the scores of the top features based on the threshold. So if you crossed a certain threshold of anomalousness, then we would rank you enough, so we would use that feature in the scoring algorithm. And we'd only show the top 50 domains to the analyst. So let me show you how it actually looks like. So we got 67% accuracy on the 50 domains. Now, that might not sound like a lot, but when you say that we had to assume that there were even malicious domains at the firsting point, that's not a bad number. And actually, when we manually verified these domains, we were very happy to realize that they're all actually part of, well, the ones that were right about were actually part of CNC control systems. So this is a very basic manually reviewed process. So how do you actually manually review a domain? What you do is you actually go to Google or to open source intelligence sources like VirusTotal, and you check out if the domain has been labeled by someone else. If you can't do that, or there's no record because it's a very new domain, you can just actually go to the domain yourself and look at the headers and see it. Often you don't need to do that. You can just, the open source intelligence community is so powerful that within days you'll have evidence of most of these domains already in the feeds. You can also inspect the device of the user. If you want to verify that a certain domain is malicious, you can just look at the device that actually triggered this access to this domain and look at if there's something anomalous in that device. We have another tool to monitor a list of processes that are running on this device, and using that we can actually confirm that something is wrong on that device. And the last thing is actually question the user. You can just talk to the user and verify that if they did something wrong. If they downloaded a new piece of software, that might be part of it. But this is a very manual process compared to a lot of the feedback loops that you would want to have when you compared to the feedback loop when you label spam. You just click spam. So this is a very lengthy process, but it is the only way to work in the security world, where attacks are not made of single events, but are actually made of multiple events comprised as one attack. And I wanted to show you the screen, because actually talking about the model without showing you how it looks like is a bit difficult. So this is just the screen showing you all the list of domains, and I don't know why they're blurred out. I think RSA wants to protect the identity of the attackers. I'm not sure why. So, but this is the screenshot I found online. You can see they're just ranked by the score, and you can click on the report view and investigate. And you can, when the user clicks investigate and click navigate, they will go to a screen that pulls up every piece of traffic that this domain has been doing. But if you click on the report, we give them this report, which is our data science report. And basically, we didn't just give them the score, because we know that security analysts are not happy just getting a score. They want to understand why you gave them that score. So we gave them the raw features, so the number of distinct user agents and the number of unique URLs accessing a specific domain. But we also give them, in addition to the score, the raw number, and we give them, when we color them, so we know which ones were activated, which ones were above the threshold by the color red. And we also give them just additional information that we thought would be helpful to prove our point, because we don't want to send the user to another screen after we want to persuade them that this is actually a malicious domain. And if they are persuaded and they want to move forward, there's an investigate button that lets them actually look at all the traffic to that domain, so they can actually find the users infected and move on and in mitigating this type of attack. So this is my take-home message to you when you're building a data science product, specifically in the security world, but even elsewhere. So the first thing is to focus on the user's pain. When you choose the project, focus on something that the users really care about. If you don't find something that users really are affected, if you can't find the pain of the users, there's no point in building something. And that's, I think, the major point for us at RSA. The second lesson is short development cycles. When you build something like this, this took us, I think, 2 months to prototype internally and maybe 8 months to get to production. And later, it took even more time to actually deploy at customer sites. So you need shorter iterations to get to the results you want. You want to get the feedback as a data scientist much faster so you can improve your model, you can add more features, you can change things. And you need to be able to do that. You need to create a system and the organization that supports that. And the last thing is regarding big data tools. So I really love big data tools, and they're very powerful. But you don't need to use them if your data is not in the volumes. So I think there's a good rule of thumb around when to use a big data tool. And if you can fit your data set in the biggest instance that Amazon sells, then you don't need big data tools. So if you can fit it in one box, then you don't need to use, because the things you miss by moving your data from SQL, from single memory, single node computing to distributed machines, you lose so much in your agility and your speed of development that you'll pay for it. So if you need to, then that's fine. But if you don't, then it's a great lesson to take. And lastly, we're hiring, so if you're a data scientist or a DevOps guy, please go to this URL. Questions? Questions?
So you don't mention neural nets in your presentation. Is there anywhere within the kind of security domain where it makes sense to use neural nets?
Yeah, so that's a good question. I think when we evaluated the different models, I took the sort of data sets that we extracted using the Hadoop, and that actually after you extract the features on a single box, after you extract the features using Hadoop cluster, you can actually run different, because it's not that big. When you extract the features, it becomes like a few megabyte file. So you can run different models in your machine. But I think for us, it was difficult to use these different algorithms to show if it's helpful. And I think we wanted to find a model that really that we can explain the users how the model works, and that we can have predictable results. And for this type of anomaly that of unsupervised labeled data, we couldn't use neural nets. But I think in other domains, not the APT detection, but other domains in security, there's quite nice developments around neural networks and specifically deep learning. I think anomaly detection is not one of them, but when you talk about traffic detection, so when you try to label the type of traffic that goes through a channel, there's been work around, I think the Chinese government and some researchers in China are really interested in knowing about what is the type of traffic going on, and they've been doing great work around that. And the second thing is in detection of malware. So let's say you have a data set of malware samples, millions of executable files labeled as benign or malicious. That type of problem is a great problem for deep learning, and there's work around that, I think, done at Microsoft to automatically label samples of malware where they statically extract features and just train a model on that, and they've been doing great work. If you're using Microsoft antivirus, you probably have patterns that were generated by this model. Thank you.